Let us discuss our new topic, that is photochemistry. So what do you mean by photochemistry? So as we say, photo is nothing but light. Here chemistry, some reaction is going to happen, right? So means what here? Photochemistry is nothing but what? Some radiations. There will be interaction of radiations with chemical reactions. We call it as photochemistry. So let us see the definition over here. The definition of photochemistry is nothing but what here? Interaction of radiation with matter of photochemistry, means which is a branch of science which deals with chemical reaction by absorption of radiation. And here mainly which type of radiation we are going to take? UV and visible radiation with a wavelength and under the reason 8000 to 2000 angstroms. So this is nothing but photochemistry. So generally this photochemistry consists of two types, that is photophysical process and photochemical process. So what is photophysical process and what is photochemical process? So the photophysical process is nothing but what? The substance will absorb light and there will be no change, no chemical change depending upon the light. Means what here? There will be no chemical change. That one we call it as photophysical process. Okay, so means for depending upon the light, when a substance absorbs light, so they do not undergo any chemical change basing upon the light that may be emitted. Okay, so the light may emitted, so when you pass rays it may emit back. That one we call it as what here? Photophysical process. So generally this photophysical process consists of three types. The first one is here, if the absorbed light is having some energy, means what here? You will be having the excited state and ground state. So in ground state there will be no energy. When you apply some energy, what happens? Immediately the atom or ion molecule will excite to the excited molecule. So here same way will happen. When the absorbed light is having some amount of energy, then the electron jump to the other orbit, or it may leave the atom completely. Okay, so this is the first point. And coming to second, if the absorbed light is emitted instantly, means what? Immediately if the absorbed light is emitting back, returning back, that one we call it as fluorescence. If suppose the absorbed light is emitted after some time, so after some time it is returning back, that one we call it as what here? Phosphorescence. So these are the three types of photophysical process. So coming to here, photochemical process. So the photochemical process is nothing but what? When in the absorption of light there will be some chemical change, that one we call it as photochemical process. So let us take an example here. Here H2 plus Cl2, in the presence of light it is going to give HCl, and 6CO2 plus 6 photosynthesis process, or as we know common everyone. So that is light, in the presence of light and chlorophyll it is going to form the carbohydrate. So these type of reactions, when some radiations are passing, it is giving some chemical reactions, that one we call it as photochemical process. So this is nothing but photophysical and photochemical process. So generally we are having differences, that is photochemical and thermochemical reactions. So photo is nothing but what? Light. Under light the reaction is going to happen. Thermochemical is nothing but what here? Under heat it is going to happen. Okay, so here the presence of light is necessary to take the reaction. We can say the presence of light is not necessary here, heat is required to take the reaction. So here there is no effect on the rate of photochemical reaction. We can say why? Because here intensity of light, the wavelength, will depend upon the rate of the photochemical reaction. But coming to here, it will be have a some effect on the rate of reaction, thermochemical reaction. So when you're speaking about the thermal energy, so it is not having negative cases. When coming to here, there will be having a in thermochemical reaction negative cases. So this is nothing but difference between photochemical and thermochemical reactions. And also we are having here in this reaction. So whether the energy is gained due to the presence of the UV light, we can say here, in this reaction due to the presence of collision of molecules, we can say, under heating condition, whether it is exothermic or endothermic. So here only single selected species means what, here it is going to excited state, and it is not going to depend on that state, and it is going to return back on that state. But in this reaction what happens, absorption of heat increases, so all molecules is not going to have this selectivity. These are the differences between photophysical and photochemical process. So this is about photo and thermochemical process differences. Now let us see about quantum yield or quantum efficiency. So what is quantum yield or quantum efficiency? So quantum yield is nothing but here. So generally we are having number of molecules of a reaction. So you are having reactant and product. Okay. So how much molecules at a given time? For example, certain time I have given. How much reactant and product is observing when light is going to observe. That one we call it as quantum yield. To determine the molecules reacting in a time, that one we call it as what here, quantum yield. So according to Einstein law of photochemistry, what we can say, every reacting molecule observes some amount of radiation, some amount of light, even small minute of light radiations. Then number of reacting molecules should be equal to the number of quantum observed. Means what here, the reacting molecule should equal to number of light. That one we call it, that efficiency will be always unity. Okay, so it is denoted by phi. By this what we can say here, the ratio of the number of molecules reacting in a given time to the number of quanta observed in same time, we call it as quantum yield or quantum efficiency. And we can say here, number of moles reacting in a given time by number of Einstein observed in same time also we can say. Why? Because the reacting molecules we are saying, for example H2 plus Cl2, there will be 2 moles at a given time, and how much light it is observing. So that is nothing but here moles and here Einstein. Okay. And here small amount of light which is observing a large amount of reaction here, and large amount of light can observe a small amount of reaction also. So this is nothing but what here, this is nothing but quantum yield. In this we are having primary quantum yield and secondary process. It consists of two types of process. So first one is primary process and next one is secondary process. So primary process is nothing but what here, when a light is observed to a molecule, so it is going to form a activated molecule. What is activation energy? We have discussed in the previous class. Activation energy is nothing but more energy is required, okay, to form the reacting molecules. That one we call it as activation energy. And coming to here, when light is going to observe molecule, it forms an activated molecule. So that activated molecule formed due to the presence of light, it may react or it may not be reacted. That one we call it as what here, primary process. By taking under the consideration of primary process, we are going to speak about the secondary process. So the secondary process is nothing but what here, the activated molecule which is formed during primary process, it may undergo some changes. What are those changes to complete the reaction? So first it form the final product, and it may partially or completely deactivated we can say, or it may cause any reaction of many molecules to form chain mechanism. Okay, so these are the two processes. What is primary process? When you observe some light, it is going to form a molecule. That molecule may form they may react or they may not react. So by taking consideration into the primary process, the secondary process will complete the reaction. So it may give the final product or completely deactivated product, or we can say chain reaction. Chain reaction is nothing but free radical mechanism is going to happen. So whenever we are using the symbol of H mu under chemical reactions, it undergoes light. It is absorbing some light. So that light indicates what here free radical mechanism it is going to undergo. So what is free radical mechanism here? It undergoes 3 steps. One is chain initiation, chain propagation, chain termination. The 3 steps we are going to discuss in this quantum yield. So we are having low quantum yield and high quantum yield. So let us see here low quantum yield. So low quantum yield, we have taken over the example of here H and Br, hydrogen and bromine. So let us see first of all primary process. So when it is going to absorb the light, 1 quantum of light is absorbed per molecule for the reactant. So it is going to form the activated molecule, that is at Br2. Let us take Br2 here. So the Br2 in the presence of light, what it is giving? Br star and Br star. Br star, or we can say Br radical and Br radical, which is also known as chain initiation step. And it is having the quantum yield is how much here? It is having phi is equals to 0.001. So let us take that is the second one. Means what? It formed the molecule, activated molecule. So secondary process, what happens? So the activated molecule of the first process, it will form another molecules. Okay, so the means what we can say, sometimes the activated molecules will deactivate also. Yes or no? Deactivated by collision. When you collide these 2 molecules, so what happens? Sometimes it may react or it may not be react. So when the reaction, so when light is falling, it is forming an activated molecule, and the molecule is going to form the collision. Collision is nothing but what here? 2 molecules are colliding. Then after that, emission of radiation before the reactant undertake place. Means what here? The quantum efficiency is very low. How you say the quantum efficiency is very low? Why? Because it is absorbing the heat here. Endothermic reaction. Endothermic reaction is nothing but what here? The heat observation, we call it as endothermic reaction. So let us take one activated molecule, that is Br star, and take H2. So H2 we are taking, which undergoes endothermic. So it is giving here. So these steps indicates, these 3 steps indicates chain propagation. What is chain initiation? When molecules colliding in the presence of lab, it forming a new radical, and the radical is combining with the molecule, it is giving again radical. Like that the radical is continuing. Chain termination is nothing but what here? Combination of 2 radicals, it is going to give the molecule. So let us see here it is going to observe the endothermic reaction. So means what we can say here? When Br radical is combining with H2, it is giving HBr plus H radical, and in the same way the H radical when you combine with Br, it is giving HBr plus Br radical, and again this H radical plus HBr when you react, it is giving H2 plus Br radical. So means what? When you observe these 3 terms, it is giving the radical. So here also if you observe these 3, so when you combining radical with molecule, it is giving again radical. So this is called chain propagation step. So at this process what happens? It is observing some amount of heat. That heat indicates endothermic reaction. So that's why the quantum efficiency is very low here, and the value is also here 0.01 we are getting. So finally what we have to get? The final product. So how we are going to get final product? By combining the molecules, activated molecules, that is Br radical plus Br radical, it is going to give the Br2. This one we call it as what here? Chain termination step. Okay, so the first equation we call it a chain initiation, and equation 2, 3, 4 we call it a chain propagation, and equation 5 we call it as chain termination step. So here the quantum efficiency is very low. That's why we are saying what here? It is having low yield quantum efficiency. Now let us discuss about high quantum yield or photochemical reactions. So high quantum yield is nothing but what here we have taken the example of here H2 plus Cl2, which will give rise to HCl in the presence of light. This is also here the quantum efficiency we are going to have how much, 10 power 6 to 10 power 4. Okay, so what is the primary process? When it absorbs light with a wavelength 4800 angstroms, we are going to get over here is Cl2 plus H mu gives rise to Cl radical plus Cl radical, which is known as chain initiation step. And coming to secondary process, what happens? It undergoes exothermic reaction. So of course we are using here light reactions. Even though we are using light reactions, it is undergoing thermal conditions. So means what? It undergoes exothermic, means it releases the heat over here. Means what happens here, the Cl radical is reacting with H2, it will form HCl plus H radical. After that again what happens here, this H radical again combined with Cl2, it will form HCl plus Cl radical. So here the Cl radical which is formed in the primary process, it react with again what, H2 molecule to form HCl and H radical, and again this H radical react with chlorine, it forming HCl and Cl. So means what, these two steps, only two steps it is going to form. It is having only two steps possible. So the two steps we call it as what here, chain propagation step. Finally what happens, this Cl radical will form the Cl2. That one we call it as termination step. So by this what we can say here, whatever it is forming, it is a instantaneous immediate reaction at the quantum yield 10 power 6 to 10 power 4. That's why we call it as it is a high quantum yield. So this is nothing but what here, this is nothing but quantum yield or quantum efficiency. So next one we are having Jablonski diagram. So let us see what is Jablonski diagram. Jablonski diagram is nothing but what here, which will explain about the energy states of the molecule. We call it as what here, Jablonski diagram. Okay, so the Jablonski diagrams will explain about energy transitions in the presence of light of the molecule. We call it as Jablonski diagram here. So we are having S1, S2, T1, T2. Okay, so when you take only ground state, that one we call it as S0. If you take one more state, that one we call it as S1. If you take one more state, that one we call it as S2. So means what, these all energy states in the presence of light. So here the energy states are S1, S0, S1, S2. We call it as singlet state, and T1 we call it as triplet state. Okay, so in here I have not entered any electron or atom. So when I entered a electron here, when electron I have placed over here in the ground state, so then what happens, it in the presence of radiation, so there will be very less transfer of electron radiation to an unexcited molecule, or transfer of excited electronic energy into thermal energy. We call it as what here, non-radiative process. Okay, so means what we are saying here, when electron from ground state to excited state is happening in the presence of heating condition, that one we call it as non-radiative process. So this is nothing but Jablonski diagram. So this is S0 state, this is S1 state, this is S2, and this is here triplet state. Okay, if you have been seen here, so here what happening, let us see here. So when you apply some amount of energy in the presence of light, what happens, it is going to absorb in the from ground state to higher state. So it is not staying at the time. Immediately what happening, it is returning back to the S2. This is, let us think, this is ground, this is state. Immediately whenever it is returning back to the singlet ground state S0, in the presence of light, this one immediately it is returning back, no? So instantaneous reaction we call it as fluorescence. So this one we call it as what here, fluorescence. Okay, whenever it is getting from S2 to S1, Under thermal conditions, under heat conditions, that one we call it as internal conversions, that is S2 to S1. So if support from here to here again it is getting, that also undergoes here internal conversion, means in the same reaction it is going to happen. But from singlet to triplet, in the presence of light, from one state to another state it is crossing in the presence of light, that one we call it as intersystem crossing, means which undergoes triplet state, that one we call it as what, intersystem crossing, that is S2 to ST2 or S1 to T1. So here again what happens, from T2 to T1 again it is coming, that one we call it as internal conversion under thermal. Internal conversion will happen only under thermal conditions. Okay, so then what happens, singlet state transfer to triplet state with lower energy, that one we call it as intersystem crossing. And here the light from triplet state to S0 state, this one we call it as what here, phosphorescence. After some time again what happens, the light is coming back to ground state. So this is nothing but Jablonski diagram. Next, so let us see here, fluorescence, phosphorescence, chemiluminescence. Fluorescence is nothing but what here, the substance which absorb light and emit back immediately. So means what, so whenever the light is observing to the higher state, it will not stay back and immediately return back to the ground state. That one we call it as what here, fluorescence. At different wavelength it is having fluorescent. So the fluorescence diagram, if you have been observed, this is absorption transitions, this is excited. So means what we can say here, when light is cut off, the fluorescence is not going to explain in the presence of light. So by this it is explained on the presence of light. So when electron excited here to the molecule, it immediately jump to the lower level. So some part of light is absorbed in the form of radiation or wavelength. Example we can take it over here is vapors of sodium, iodine, mercury and uranyl sulfate are the examples. Next, phosphorescence. Phosphorescence is nothing but what here, it is nothing but the substance which absorbs light and emit for some time, means it will take some time to return back to the ground state. That one we call it as phosphorescence. Even though if we not pass any light, then also the phosphorescence is going to act over here. So here the phosphorescence is a slow fluorescence, we can say here. Why? Because the phosphorescence mainly observed in solids, because in solid molecules are tightly packed, it is having very least freedom moving of electrons. That's why it is going to jump back slowly after some times. Let us take an example over here, sulfate of zinc, zinc sulfate and alkaline earth metals. Alkaline earth metals is nothing but in S block group 2A elements we call it as alkaline earth metals, which is combining with here heavy metal sulfite. Okay, so these are the best examples for the phosphorescence we can say. So for example we can say here luminescence also for pointing watch dials, so and also electrical switches. So these are the examples for phosphorescence. Chemiluminescence. Chemiluminescence is nothing but what here, emission of light in chemical reaction at certain temperature. In the presence of temperature, it is going to form a chemical reaction and also light. That one we call it as chemiluminescence. Example we can take it over here is light emitted by glowworms and also oxidation of proteins luciferin by the atmospheric oxygen in the presence of enzymes. So these are the examples. And also greenish blue glows by using Grignard reagent. So this is nothing but chemiluminescence. Next one is photosensitization. Photosensitization is nothing but what here, substance which can absorb light and which will give you some change without taking part in the reaction. Means what we can say, some third substance is coming and adding over here, which also known as foreign substances. That one we call it as photosensitization. So here dissociation of the hydrogen molecules we can say here. Here Hg will give activated molecule. The Hg when combining with H2 it is going to give Hg plus 2H. This one we call it as activated molecule. Whatever it is forming, that one we call it as photosensitization reaction, and we can take it photosynthesis reaction also here in the presence of light. And the last we are having the topic over here is photochemistry. So there are two laws of photochemistry. One is Grott's-Doppler law, another one is Einstein law. Grott's-Doppler law is also known as photochemical activation we can say. It was discovered by Grott's, and by doing some experiments he states that only radiation of light which can absorbed by the substance will give a photochemical change. That is nothing but Grott's-Doppler law. Means what here? When light is going to observe the reaction, it will give some type of chemical reactions. So but it does not give, some reactions will not always give you light reactions. So then we are having some conditions. What are those conditions? The light can be converted into heat. For example, in case of potassium permanganate solution, the light is absorbed strongly here, but there is no chemical change, right? And second condition, if you have it, the light is re-emitted, means it is coming back. So means what happening here with the difference of wavelength, it is giving fluorescence and phosphorescence. So sometimes what happens, the observed light transferred from one state to another state to form a chemical reactions, means that one we call it as photosensitization. So means what, these three things is going to happen. So that is nothing but Grott's-Doppler law. Then coming to Einstein. So what Einstein has observed, some amount of energy to a photochemical reactions is observed. Means in the presence of light, it is giving some energy to the reactions. That one we call it as Einstein's law. So each quantum of radiation will have to activate the molecule, means they have to collide the molecules, which depends upon the primary step of chemical process. That energy absorbed per a molecule, we have given the equation E equals to NH mu, or we can say where mu is frequency of light. So frequency of light is velocity of light by lambda, wavelength. This one we call it as Einstein's law. And also here Avogadro's number we are having, which is a constant. So here wavelength of radiation is always equals to the energy absorbed by 1 mole of substance. So this is nothing but photochemical equivalence, Einstein's law. In the next class we can see the thermodynamics. Thank you.